All right, thank you everyone for inviting me. It's a pleasure to give a talk here. So my talk is about Pointwise Ergodic theorem along the primes. It's a mixture of a few results, let's say. So here is hopefully my goal to cover. I don't know, I mean, don't worry, it's like too much, but yeah, so I start from measure preserving system, what it is and what can it do. And then I'll mention the Pointwise Ergodic theorem, and then which is like abbreviated by PET. And then PET, I will talk about Pointwise Ergodic theorem along the primes. I give a dense argument, which is basically suitable for the original Pointwise Ergodic theorem. Then I'll try to start reducing the problem into a maximal estimate at the end. I just barely touched like mentioned the techniques that you can do for proving these maximal estimates. I give a toy model for what is like the operator, what's like the kind of operator that we have. Then endpoint result and a structure theorem is like a result that is really very related to this topic. Then I will a little talk about number fields, like how to go for like a little more general setting. And hopefully if I have time, I will talk about the bilinear theorem, the recent work of Cruz Mirektao. And also I'll try to talk about a current project of ours. And then finally, there is open problem. So there are some open problems that I want to talk. Before I start, I want to say, because I was not very familiar with the audience, so I'm sorry if I am talking about something obvious, or I am sorry if I am giving a lot of like unfamiliar kind of definitions and notation maybe. So basically, it's a little hard to give like a talk when your audience is in a broad situation and you want to talk about something that is very analytical. So hopefully you like it. All right, so here is the first thing that we want to say. So assume that you have X, A, and mu to be a probability space, and you have T to be a transformation from X to X, such that it is measure preserving, in the sense that if you have a subset, then the measure of this T inverse is equal to the measure of B, which means that this T preserves the measure. So assume that you have this kind of transformation on equipped with your probability space, then this quadruple of X, A, mu, T, which A is like the sigma algebra that you have. So X, A, mu, T will be like a measure preserving system. And one of the famous examples for a measure preserving system is, which we call it circle shifting, is basically you pick your set to be an interval of 0 and 1, and you look at the sigma algebra, assume like that's very, very common, like let's say Borel sigma algebra. You pick a fixed number inside 0, 1, and then your transformation is just the shift basically by alpha. And why do we call it shift? Because look at X as an angle, little x here. Look at it as an angle. Basically what this transformation does is just basically shifting you by alpha. So this transformation is, this quadruple is a measure preserving system. So also we have a notion of ergodicity, which means that a transformation is basically ergodic if you have a subset such that is invariant almost everywhere. I mean, this almost everywhere notion means that for almost every point you have this, which you can write it this way as well. But anyway, if you are invariant under your transformation, then your set should be trivial in the sense that either your measure is 0 or 1. And you can see, I mean, it's a good practice to check to see the circle shifting is an ergodic transformation. All right. So here is the classical ergodic theorem, which is due Birkhoff and von Neumann. It's in the 30s. So assume that you have this quadrupel that is a measure preserving system. So it's a probability measure, again, equipped with the transformation that respects the measure. Then look at f to be a function in this set, and assume that f is in LP. For those who forgot the definition of LP, it means that this integral is basically finite. And then look at this averaging operator, which is basically you average over evaluations of f, which I will mention what is this notation means. I mean, in dynamical system, you usually use that kind of notation, but it's just this. So basically you have your x, a point in your capital X, then you can apply Tn on it, which is like a transformation. You get another point at x, and then you evaluate it for function f. And then you can do it for different n and average on that. You get an average. So this ergodic theorem means that this SNT converges either almost everywhere or in norm. And then for p bigger than or equal to 1, remember that this f is in LP, which I am saying that if p is bigger than or equal to 1, you get the convergence. So one thing that is important is that the focus of this talk is for almost everywhere or pointwise convergence. So we are interested in that. And also I want to say that this in convergence in norm was proved by von Neumann, and almost everywhere was proved by Birkhoff, both of them in 1930s. A good question would be, what is this limiting point? What this limiting point is, in the sense that, okay, this converges, but converges to what? There is a very rich direction that studies these kinds of questions, which I'm not talking about today, but I just say that if T is ergodic in the sense that we defined it here, if your T is ergodic, then SNT, so for T to be ergodic, then, sorry, if T is ergodic, then SNTF goes to integral of f. So that's the limiting point there. And obviously it's a constant. So here is another way to look at the ergodic theorem. Here is the set x that you have. You pick a beacon x and you look at the orbit. So you evaluate it at t squared, tq, t4, and you got a bunch of points. And then you evaluate each of these points by f in f, and then you take the average. And this ergodicity, which gives you the integral, means basically that if you average over time, you will eventually tend to your average over a space. So that's the kind of situation that we have here. All right. So
could you explain this a bit more? Average over time goes to average over space.
Yeah. So basically, this averaging, you can look at it as average over time. For example, assume that your x is the time variable, and your Tn is a shift by n. It means that you have f of x minus 1, which is 1 second before, for example, f of x minus 2, 2 seconds before, 3 seconds before. You see, you take all of these functions, you take the average of these variable over time, and what you get is average over a space in the sense that you take the integral, which is like the area. That's kind of the situation that we have. So it's like a not very exact way of saying something, but it's something that is kind of famous in the community. So that's why they call it this.
Also, when we're integrating f, the measure we're integrating with is a probability measure, right? It's
it's d mu. I didn't write it, but yeah, thank you.
Okay. So this ergodicity means that if you repeatedly apply the operator T to X, you're going to visit every point in the place.
It's kind of like that. Yes, yes. Informally, it's like that. So basically, it means that your orbit becomes kind of dense.
Mm-hmm. And everything that is measure preserving would do that.
Sorry?
Every operator, the only condition you need to have is that the operator be measure preserving, correct?
Oh, for this theorem, you only need measure preserving.
All right, thank you.
Yeah. So, the next thing that we want to talk about is ergodic theorem along the prime. So basically, what I'm saying is that the same condition happens, so you have the same measure preserving system, and you have your F in LP, and then you only weighted it by von Mangold, or you can just write the primes. And by the way, for those who are not very familiar with the von Mangold, it's kind of like an indicator of prime, which you can write it for n for prime powers you get log p, and otherwise you get 0. And then you can also have the almost unobviously norm, but almost everywhere convergence for p bigger than 1. And I want to make sure I want to mention that this p bigger than 1 is different from p bigger than or equal to 1, so the endpoint doesn't work here. Okay, actually a very quick version of like some steps in proving this theorem. I'm not going through the details, and there are other research items as well, but I'm just mentioning a few. So here Bourgain proved it for the first time for this range, and then Viardel tried to completed the proof for the whole range, but there was a very small issue in it. Mirek, based on his work with Stein, proved this theorem for p bigger than 1, and even a little stronger version, which we call it variation. We proved the sharp weak type for this, and then Lavitore proved that for p equal to 1, it is actually not correct, so it doesn't converge. And again, this question also is we can ask that what is the limiting point there? It's not as good as the usual one, because primes is a little more complicated, but the limiting point can be achieved to the integral again if your t is strongly ergodic, in the sense that not only t is ergodic, t squared should be ergodic, t cubed should be ergodic, t4, and so on. All of them should be ergodic. And if you have that condition, then you have the convergence as well. And
excuse me.
Yeah, please.
So T is indicator function of terms of Van Mangold. I don't understand it. How does that work?
Yeah, sorry, maybe I went too fast. So T is your transformation in your ergodic system.
Mm-hmm.
And von Mangold function is this definition.
Yeah.
So are we good? Is there like any? So for example, if you want to look at it as shift, it's like this: f of x minus pn. You are just looking at the primes, the shifts of primes.
But we know the sum of Van Mangold function very well, the average of it.
Okay, yes.
I mean, so what does it say about prime? Is it just an example, or is it like, are you trying to say something about distribution of prime numbers?
It's not exactly distribution of prime numbers. I will give you a couple of application in number theory later, but the theorem is basically saying that this is the whole theorem, which is inspired by Furstenberg. So Furstenberg asked that in this theorem, if you have like this average over time, but instead of the whole time, you have the prime time. So you only average over the prime numbers. Okay. Then you have, so if you look at this picture, you start from x, tx, you have a bunch of points, right? Then, for example, the T2, T3, T5, T7, I am just adding these guys. I'm not looking at the rest. So the question is that, do we converge again or not? And the answer is this. All right.
Okay. Thanks.
So no problem. So now I will talk about a dense argument, which is suitable for this average. So basically, if you have an ergodic system, a measure preserving ergodic system, and if you have your function f in L2, so basically I wanted to prove it for f in LP for p bigger than 1, right? One way to do that is bigger than or equal 1. So one way to do that, if you look at f2, then the whole L2 can be written as 3 ways. So as sum of 3 functions. The first function is the invariant one. So it's invariant over this t that I fixed. The second function is basically a bounded function, and you have the co-kernel. That's what we call it, this set. And then the last one is because you are talking about L2 and sorry, this was L1. I'm sorry, this is typo. So, sorry. So basically, this epsilon is coming from the fact that your f is in L1, and this guy gives you a function in L2. So L2 is dense in L1. So the point is that every function in L1, in L1 or any LP can be written as an invariant function, a co-kernel function, and a very small error term, which if you pick delta before, then you can say that your error is less than delta, let's say. It's a little analytical to talk about it, so I want to skip quickly. But the point is that for those who like this kind of writing, you can also write, sorry, this is again L1. You can say that L1 is closure of this one plus closure of the co-kernel plus the invariant set. But anyway, why do I use this character decomposition, which I encourage you if you are interested to try and prove it yourself. But why do I do that? Is that if you have this version, this G and H minus TH can be very easily handled, in the sense that if you have G, for example, you put G instead of F here, and every T and F becomes just G. So basically every T and G becomes G because T is invariant with, G is invariant under T. So you have N of them, and then if you add them up, you get just G for the average. And I know I have like complete control of what is G, so this part of the convergence is okay for me. And for H minus TH, if you put it here, then you will get Tn minus Tn plus 1, and that begs for a telescopian sum. If you do that, only the first and last term will remain, and H is bounded in the sense that it is in L infinity. So you get a bounded number over capital N. When N goes to infinity, it goes to 0. So this part gives you 0. This part only gives you G, which I have total control over them. The only remaining part is epsilon, which is ironic because usually the error term is the one that you can ignore. But here, the only thing that remains is actually the error term. So now, a straightforward argument shows that in order to prove the convergence of this SNTF, you need to only prove that the convergence is true for SN epsilon, basically SNT epsilon. And for that, it's straightforward, but you can see that you need to just prove that this measure is 0. So measure of this set is 0, which basically gives you Cauchy, and Cauchy gives you convergence. So in order to prove that, you can just, the left-hand side by triangular inequality is less than just one of them. And then if you believe me with this question mark inequality that this part is true, then your epsilon 1 by definition is less than delta. Delta goes to 0. So basically you get the 0. And the moment that you get this measure to be 0, you get the convergence as well. So by this very, very like elementary analysis argument, you can reduce your convergence problem to this inequality, which I write it in a little better version, actually in a version that Borgen wrote it. You can show that convergence of SNTF reduces to the convergence of this function. So let me just, here was the definition of SNTF, which was the average over f in time. The only thing that I'm trying to do is to take the supremum over all of these ends, and then look at the LP. If you get that this LP inequality is happening, then you get the convergence of the theorem. And that's what we call it. I mean, this inequality is called maximal estimate in our. So basically, all I'm saying is that in order to prove the ergodic theorem, you need to just prove this inequality, because if you prove this, you can have this question mark, and this green argument gives you the convergence. All right. So the important thing is that this very elementary argument doesn't work for the prime, because for h minus th, if you apply it here, you can't use the telescopian sum anymore, because primes are not differed by 1, but so you will have something else, which means that you need to do something else actually. What Bourgain did is that he first said that, okay, instead of the whole integers, I can just look at a sparse set of them, which is like, I don't know, you can say just dyadic powers, it doesn't matter. And then in the next step, he uses some oscillation inequality, which I won't go through, but the point is that after this step, you can reduce your operator to a maximal estimate. So this step that Bourgain did here is equal to what I did here for the actual integers. Okay, so for the prime, you need to do something else, which Bourgain did. And now anyway, for both Sn and An, I only need to prove the maximal estimate. And there is a transference lemma, which is very, very important notion in analysis, which basically states that if you can prove it for a shift, you can prove it for every transformation. So this maximal estimate, in order to prove the maximal estimate for every transformation, which is actually the only job that we need to do, we can only prove it for a shift, and that's okay. So the same is true for both Sn and An. I wrote them in different colors so that you see both of them. Here is An for shift. You can see it's exactly like the form of the convolution that we have. So basically, I actually wrote it as a convolution, and this is just the kernel that you have. All right, so maybe those who are more like interested in Goldbach setting and this sort of thing have already seen these kinds of convolutions. So now, all in all, I want to like kind of summarize what I did so far for proving the primes, for example, is that I need to prove this maximal estimate, which is basically the supremum over my convolution operator. Yeah, please.
Something. When you're taking shifts f of x minus n,
okay,
then are you applying the operator t in reverse n times, or what is the actual ground space that x is coming from? What do you mean by x minus n?
Oh, here, yeah, that's a very good question. I'm sorry that I missed that. So f now is coming from z to c. So here,
okay.
when I'm saying LP, so when I'm saying G is in little LP, I mean little LP of Z. And when I'm saying here G is large LP, I mean large LP of any probability space.
Okay.
Okay. So now X is actually integer.
Okay, so then you can subtract.
Yeah, I can just subtract and do it again and again to get different shifts. And that's kind of like a convolution.
T is the shift when you little L you work. T is the shift, right?
Sorry,
in this theorem that you write, T capital T.
Okay.
What is the transformation?
Yeah, transformation in general is a measure preserving transformation. Okay, so it's just a map from X to X that respects the measure. But here in this specific case, it's just a shift. So T of X goes to X minus 1. There is a little more explanation on it, which I guess time doesn't allow me to go through it. But It's related to Forstenberg principle, basically. But yeah, so basically the transformation is a shift. That's only thing that we need to know. I mean, for the little LP at the moment. Okay. So now,
Sorry,
yeah, please.
and what is the measure in this case?
Yeah, that's a good question. Okay, so you can use counting measure, and for the actual measure, it's upper Banach density. I have it at the end of the talk, but I was thinking that if I go through it, it kills a lot of time. So I don't know, if you trust me that there is a measure, is kind of like counting measure, that would be great at the moment.
Okay, but it is not measure preserving, I think.
So yeah, exactly. So it's a Follner sequence, which is basically the gives you the upper Banach density, basically. For example, for prime, it is 0. For even number, it is 1/2. For multiples of 3, it is 1/3, and so on.
Okay, thank you.
No problem. All right, so now here is the final reduction that I had. So I think that because of time, it's good to not go through this example, I guess. I'll go back to it if I have time, let's say. But let's say that so far I have this Kn, which is my kernel, basically. And then I want to prove this maximal estimate. One way to prove it, I mean, it's a typical way in harmonic analysis to prove some operator has some LP boundedness, like what we have here. In order to prove the kind of situation, you basically try to make this Kn replaced by something very, very familiar for you. For example, prime is a very bad choice for us because we really don't know much about prime. Yes, I know that we have a lot of like distribution argument, but it's not enough in this application. So we need to change it. And in order to change it, it's better to pick examples of F there and see what will happen for that. For continuous version, if you are working on continuous setting, when you have like a point, you just try to like zoom in here for this point and see what will happen in this function when you have this transformation. In the discrete setting, when you have the z, the integers, it's better to go. So equivalent of zooming in the continuous setting is to go to the small progressions, in the sense that you have a progression and then you look at points here, like points of this progression as time goes, something like that. So anyway, if you do that kind of observation and look at, for example, this example, which I will jump for now, if I have time, I will go back to it. You'll see that you can evaluate this Kn, okay, as basically a sum of very small progressions of the Mobius function over Tauschen function, and then you have the Ramanujan sum here, and then you have some. It's not exactly this because I wrote a quotient here because of this. It's a smoothened version of a convolution operator, but morally speaking, it's like that. And by the way, by 1mx, I mean that it's 1 when x is in this set of 0 up to m, and 0 otherwise. So what I'm saying is that your operator, your kernel operator, which was the detector of the prime, can be also written almost close up to some error term that prime number theorem allows you. Actually, Ziegel-Wolfish. In general term, it's like more higher level version of understanding of prime. Allows you to do this these terms. So basically, it is Mobius over phi q over times tau q. So this part might be very, very familiar for those who are working with the, I don't know, Kramer-Granville model, the kind of situation. So, but anyway, you get this kernel operation, and you can prove two things for that. So basically, you prove that from L2 to L2, which means that basically KNF over F when F is in L2. That gives you one bound from L1 to infinity, which means that if F is bounded and then over F, that gives you another bound. And then, I don't know, we have Mackenzie inequality, or what we call it interpolate, whatever you are more comfortable with. You can apply that technique to get this kind of argument. I mentioned it because later we need this compact property that Bourgain mentioned. So basically, this is the kind of work of Bourgain that proves some version of what he calls it compact property. I really don't know why he calls it that, but after some point, you need to give up on the names because they are coming from a very big picture that I don't have at the moment, at least. So, but yeah, anyway, you will get these kinds of arguments, so that if your F and G are in LP, then if you convolve your operator, your prime detector operator, which we kind of studied it and understood it with this F, and then like look at it with G, let me write it actually. So you have Kn convolve F at some X, let's say, and multiply it to G, it's like a dot product. And if you compute this, you can see this inequality is happening there. And the last step of the proof for the pointwise ergodic theorem, which again, I won't go through the detail of it, is that Bourgain used some method that actually used before as well, named oscillation. And then Viardel used oscillation plus something very, very easy that Bourgain actually missed. Mobius inversion. Mirek in 2013. So basically, this one was in 1990. I guess this one is 1991. This is 2013, and I guess this is 2021 or something. So yeah, that actually shows the level of difficulty of this problem, because it's like 80 or 90 years after the actual Birkhoff theorem that got proved that we have the full proof of it. So Mirek proved a variation which is slightly stronger than the oscillation. And also we use the sparse bound to automatically gives you the maximal estimate. These are the name of the techniques that if I have time or if you have question, I can explain them a little more at the end of the talk. But yeah, so anyway, up to this point, using these techniques, we can prove the maximal estimate. And the maximal estimate gives us the pointwise convergence. As for the endpoint, if you remember, I told you that there is a counterexample. So if you have F in L1, then for any, there exist ergodic theorems, there exist ergodic measure-preserving, measure-preserving system, and L1F, which is like integrable functions, that you have the lim sup is not equal to lim inf, which means that your A and T is not converging actually. For the weak type, which means that you are a little better than P equal to 1, but something worse than P equal to any 1 plus epsilon. There are a lot of functions in this area. Then you can have this theorem of us that if F is in L log L, it's like a weak type kind of situation. Then you need GRH, and then that guy is sharp. I mean, this is sharp up to constant, that you get the convergence. And if you want it unconditionally, you get just L log S squared. But yeah, that's the kind of moral of the story, which is basically is kind of like completing the whole story of the primes, I guess, at this point. So let's see one of the number theory like applications now. So you pick an interval in the integers and look at some capital F, some subset of this interval with density delta. Then basically you can write this interval as sum of two intervals. Sorry, union of two intervals. The first one is the small, which is like the exceptional set. I can make it this tend to be as small as large as I want. But anyway, then the second one gives you this this thing, which means that primes are not visible in this set. What do I mean by that? I mean that the number of primes that are less than n, and you have also p in shifted of this set over the total number of prime is less than the density of this f, but you have a correcting factor. This t depends on, again, GRH. If you have GRH, you get 1, otherwise you get 2. So the most strongest the strongest point of this theorem is coming from the fact that I am taking a uniform bound here for all x and all n. So that's something that number theory, I mean, with additive combinatorics, you may not be able to get this level of strength or uniformity, let's say. But anyway, another way of writing it is this, that you can say probability of picking a point inside the shifted version of f in condition to picking a point on primes is less than the actual probability of f if it was equal. And if there is nothing here, it means that they are independent. But at the moment, we have inequality and we have a correcting factor here, which I just used the sharpest version, by the way. But yeah, that's one application in number theory. So this kind of Pointwise ergodic theorem can be generalized to the Gaussian setting, for example. In the Gaussian setting, assume that you have a measure preserving system, and instead of the integers act on t, you have your, for example, zi act on t. Then your a and t can be defined this way for all the Norman less than n, which is like a circle inside the Gaussian lattice. And then you can look at it this way. So you don't have the order now, but you have x, t, x, t, I, x, t, 1 plus 2i, and you just pick the primes there, kind of. And by the way, this von Mangold can be written as usual. So if n is a prime power, because you have the, this ring is very good, zi is very good, you have ed actually condition there. So if n is p to the alpha, then you can get log of, sorry, it's norm of p. And otherwise you get 0. And yeah, basically, let me rewrite this one as well, f of t and x. So here you can't, so basically it's like a combination of two shifts if you want to look at it as shift, because it's shift by 1 and shift by I, something like that. So the only thing that I want to mention is that there is a difference between this theorem and the higher dimensional version, which is basically, so basically we had like a classic version of this theorem, this Birkhoff theorem, for the, or prime theorem in the like 90s or something. But this is a different theorem because you actually respect the multiplicity condition of the structure of the ring that you are using, basically. So my point is that the meaning of prime in the higher dimensional is basically kind of, I don't want to use the word useless, but let's use it. So basically it's kind of like a useless, because something that they like to do, for example, is that you have a vector, you have bunch of elements there, and all the entries are primes in Z. But what is the meaning of this? There is no meaning on this, right? I mean, of course, it has application. Even in Green-Tao-Ziegler kind of representation, you have application there. But the actual and natural version of writing this averaging operator is when you respect the norm of the number field, and that's why this version gives you basically everything that you actually naturally can get. So yeah, and this is also convergent. Yeah.
But I mean, in case of ring extensions or field extensions, obviously there is a sort of, you can see one extension as a module or a vector space over another. Then do these averages also in ratio, or when considered for two different rings separately, and one is an extension of the other, that they are related to each other somehow? Wouldn't that be the case?
Yeah, that's actually a very good question, if I understood it correctly. So what you are saying is that if you have like a power extension of number fields, something like that, then what will happen for the averages of one of them with respect to the other one? I want to explain that, I want to mention that this is the first number field result that we have, basically, and a lot is unknown there. So basically, we even don't know how to do q square root of 2, because that's real, you have infinitely many units because of unit theorem, and then you have like this theorem becomes a lot messier. So we are trying to do that, but you know what I'm saying? I mean, what I'm saying is that even q square root of d is not completely finished now. Not completely, by far it's like far from finishing, because what will happen if you don't have Euclidean domain, even if you have just a DD, then it's a mess. You know what I'm saying? So it will be, it's like a very good question, and actually the answering this question can be a very good topic to understand, I guess.
Okay, thank you.
No problem. So
Sorry, you said
yeah.
Sorry, you said that this is converge, but to what limit it converges?
Yeah, that's actually another question that we don't know, but I guess, that's my guess, that if T is ergodic, again, it converges to integral of f. Sorry that there are a lot of unknown here, because it's like a very, very new kind of topic. Actually, our paper, this one is in 2023, I guess. This one is in 2024. So you get the idea that how, but yeah, there are a lot of open problems. Maybe like the most important one at the moment for us is this one, because if we can do this, there is a hope to work at least for q square root of d, and maybe after that cyclotomics, I don't know, but yeah, that's a very like large program.
So for the case of z, not zi, this is proof that the limit is the.
Yeah, for z you need a strong ergodicity, and then you get integral of f. So T should be a strongly ergodic. Are we good?
Also, it can be, for example, when we go into the sequence in Gaussian integers, for example, the sequence was 1 plus ni.
Yeah, that actually is a very, very important question, because if you can answer that, you can prove Landau-Wolff conjecture.
We want to track the prime numbers in this sequence.
Yeah, 1 plus, if you prove that 1 plus ni has many prime numbers, then you can prove 1 plus n squared in integers has very large prime numbers, and that's actually a Landau-Wolff conjecture. So
can we reformulate it in this, for example, in terms of this?
Yeah, I tried that. Actually, I tried this kind of situation for like 6 months or something. So far, I haven't gotten anything good, but with the emerge of like pretentious number theorem, it might be possible to like, for example, there is a paper by Motomaki and Radziwill that studies these kinds of like primes in short interval. It's basically like that. So if you have like some version of a better version of primes in short interval for a good kind of like characterization of these sectors that I wanted to talk here, then you might be able to do something for maybe not 1 plus ni. If you have both Sarnak conjecture and also GRH, you might be able to say something for 1 plus ni. I don't know. Sorry, but it's like a very, very hard problem, very challenging. So that's all I can say. But anyway, so basically for the Goldbach setting, I'm not going through it, but I just look at the picture.
Sorry,
Yeah.
may I ask you easy question? In the statement of the equality, is it 1 over n or n2? Because the normal, there are n2 terms.
Oh
in
yeah,
the
you're right. Sorry. The norm that I am defining here does not have a square root. So the radius is a square root of n.
Okay, thank you.
Yeah. So here for the Goldbach conjecture, like Goldbach theorem, if you pick x here, you can for almost every x large x that is even, you can have x to be written as sum of 3 prime. Again, because of this kind of Landau conjecture issue, you can't have everywhere resolved for the like the 3 prime that we have for the integers here. But you can have this, but the good thing is that you can pick any small sector up to what prime number theorem gives, allows you to, here prime ideal theorem, but allows you to get this sectors to be a small. But if you can go all the way to, as someone asked here, if you can go all the way to n to the minus half, you can prove Landau's force conjecture, for example. But anyway, so in the last 2 slides, I'm just gonna talk about bilinear setting now. So we talked a lot about linear one, but it's just the step 1 of a very large program, which is called Furstenberg-Bergelson-Liebman program. And this is a bilinear pointwise ergodic theorem. It's this is a breakthrough result in 2020. They proved that if you have a measure preserving system and if your F and G is in a good LPs, basically it's like equal to the condition of P bigger than 1 that we mentioned before. Then your bilinear average, basically you are trying to, it's like shifting this one with n and shifting this one with n squared. It's again converging. The issue is that the partial equality is useless in this setting. You can't use the partial equality and L2 theory that we had, but there is another way which was not available for Bourgain. That's the important thing, that why, for example, Bourgain couldn't do this. Because of this Plus-Prendeville inverse theorem that is just published in 2019 or something. So that takes care of the partial inequality. The compactness property that I mentioned a few slides before, I guess, sorry, here it was. So this is the compact property. This compactness property is also needed there. And then you need some version of adelic computations for finite fields and like p-adic fields. So you need to like evaluate some Ramanujan sums in the p-adic setting. So yeah, that's the 3 main component of this proof, which was a breakthrough at the time. But here is the kind of the new partial inequality. Let's just escape it. So now here, this is the in progress work that we have for pointwise ergodic theorem. It's a joint work with Cruz, Tau, and Travainian. So assume that you have this measure preserving system, and you have F and G that are in the same good P bigger than 1 that we had before situation. You put a von Mangold here. Then what will happen? Do you still get the convergence? And in order to prove that, you need the compact properties for the prime, which we talked about it in this talk. For Plus-Prendeville, we need to prove the Plus-Prendeville for the primes as well. The adelic argument becomes like kind of, I want to say just reduced adelic argument. So basically it will be like a bunch of reduced sums for the Ramanujan sum. And we also need some recent Gover's norm of the difference of the von Mangold and this Kramer model or Ziegler model or any kind of model that is like representing von Mangold as well. So these are like the main components of this proof. Yeah, and then one of the like nice result that, I don't know, maybe nice result that you can get from number for number theory is that you can almost prove that for a lot of even integers, at least this is what we got so far, that for a lot of even integers, this equation has a solution for a lot of ways. This is not important, but the equation itself is very important. P and R and Q and all of them are prime, basically. So this one is like the Goldbach type, but now you have this one as well. So we had Green-Tau-Ziegler theory for both polynomials and for matrix version. But the difference between this one and the previous ones is that now your variables are dependent. So they are not completely independent in the sense that P and P square are basically completely dependent. And here is like the kind of matrix equation that one gets from this thing that I wrote here. Yeah, here is the open problem, I guess. How long do I have now? Excuse me, how long do I have?
I mean, I think maybe 5 minutes.
Okay, 5 minutes is good to at least talk about this L2 theory. So before I mention the open problems, I want to say that in the L2 theory, so here it was like the usual linear case for the convolutions. When you want to write the linear case, you have actually like a convolution form for L2. Then by Parseval, you can make it like, you can take the Fourier transform of these guys. And then, and by the way, let me write here, I have L2Z, and this one is L2 of 0, 1, which is like on the circle, because my Fourier transform is actually from Z to circle. Then, so if you take the minor arc, in the sense that if this F is inside the minor arc, for those who are interested, like familiar with the minor arc definition, then you can just basically simply take the infimum of this Kn hat in our setting, in number theory setting, if you want to know, it's basically Van's identity or Heath-Brown identity, or in general, type 1, type 2 identity. Sorry, type 1, type 2 argument that makes this one very small, smaller than what trivially is. And then you have L2. So basically the moral of this story is that you get the L2 norm of a convolution operator, and you say that this is bounded by your actual L2 times a gain. And this gain is helping you at the end for all of this ergodic theorem and Goldbach type theorem, any kind of these things. But then if you have like two function here, like two shifts, like this one that we have here, then you can't do this in L2 theory, but plus Prendeville and afterward like Tau with the use of the Hornbanach theorem, they can prove that this is true for L1. So the correct one here was L2 to L2. Here it will be L1 to L2 times L2. So if you have L1 of this operator, and if F and G are living in the minor arc, which is basically a very special minor arc, but in this special setting, you get a gain of kind of like a similar gain here, maybe a little weaker. But this is enough for the convergence of Pointwise ergodic theorem. So that was the L2 theory that I missed. And that is the thing that Borgen didn't have, for example. That's what I'm saying. So here are open problems. The first one, which we discussed it, basically it's like Pointwise ergodic theorem and any kind of even norm ergodic theorem for general number fields. And there are a lot of number theory problem that opens up afterward that you can prove this for any kind of result here. Then we also have Pointwise ergodic theorem for the short interval, which is basically, I am really interested in this topic. There is a factor of strong sweeping, which means that you have both restraint from number theory for counting prime in short intervals and also from the ergodic theory, which is basically this sweeping, a strong sweeping factor or sweeping factor. The next thing is the multilinear Pointwise ergodic theorem, which I will just show you. Here it is. So here is the multilinear version. So you have, instead of just two of them, or one is linear, two of them is bilinear. Multilinear means k of them. It's for norm conjecture convergence. It's just proved, not just 10 years ago or 15 years ago, proved by Walsh in a good generality, but it's still going on. It's part of this Forstenberg-Bergelson-Liebman program. But for the pointwise, it's wide open. I mean, you have seen just the bilinear setting for the pointwise was the breakthrough result of Cruz-Mirektal. So you can see that the multilinear is by far, we are short of it by far, but yeah, that's a good question to work on. The next open problem is to do pointwise ergodic theorem for a special prime. For example, for Linux prime, for Shapiro prime of this form, Linux prime is this form. It's basically sieve theory, which is actually a nice application of sieve theory in ergodic theorem. Hopefully, I mean, that's the kind of thing that I guess. But this one is for the Shapiro prime, which is in the Hardy space now. And for example, I don't know what it's called, but Maynard prime maybe? Primes of the form that you don't have 9, for example, in your base 10 digits, something like that. All of these questions can be interesting for pointwise ergodic theorem. In general, there are a lot of number theory problems that can be translated in ergodic theory, and like the answer of them are completely unknown. which would be like the area, a very good area of topic to do research. I guess I finished now. Thank you.